guys. You can look at that wall cat shelf as I get my soup ready for tonight's live. There you go. Some of these pieces have taken quite a beating because the kitty cats do love them a lot. But there is the wall cat shelf on the wall, as well as a blue cat tree. Let me show you. There's multiple pieces. Anyways, good morning, good evening, good afternoon to everybody. Welcome all to the live. I am going to go get a sweatshirt and make my soup and then sit down with you guys, and we will do our physics live as usual. So hope to see many of you live, and bear with us. Let's see, we're gonna share the live, we're gonna get the live settings correct. I'm actually gonna get the soup going in the microwave before I go upstairs to grab my sweater. So let me do that. How's everybody doing? If you're joining, please do like, share, subscribe. We will get started here really soon with the physics stuff and whatnot. Actually going to reach into the wrong spot. Meant to get a soup. If you're joining, let me know how your day is going and things like that. I also need to get my water bottle from upstairs. Hi everybody. Thank you for joining, guys. Appreciate you. I'm just making some soup and then I will be in front of you, sitting down. Thank you for joining. Hi Emily, Arda, Shadow. God bless. How are you doing? Shadow, it's your first time. Oh, very nice. Well, it's going to be a lot of fun, so I hope you're ready. Thank you guys so much for joining. Thank you, thank you, thank you. Thank you. Please do like, share, subscribe. I'm going to start a goal for the live. Hi, Emily. Hi, Ari. Hi, God bless America. I will sit down in just a second. You gotta hang in there, Shadow. And also, you can subscribe so you can come back to all my lives, so you kind of know how this works. Thank you guys, everybody, for joining. Hello, Emily. Hello to everybody, indeed. Really appreciate everybody joining. Thank you, thank you. Here's the soup situation. As you know, we've been eating some soup recently. If you have been here before. Hi, Baji. Most likely you will see both me and Baji really soon. So hang in there, guys. Mwah. See you really soon, okay? I'm gonna grab my sweatshirt. Mama has to do a little live. Hopefully I've met some kitty cats by now. Oh, Baji! Baji, are you hosting the live while Mama gets her stuff together? Oh my goodness, there is Baji Baba. There is Baji Baba. Shona Moni. Hi, Shona Baji. There is Baji Baba. Hello, guys. I assume you heard the microwave. The microwave has my soup, so we will be eating that tonight live. And we will also be studying physics as per usual. As per usual. I just got back from the gym. Oh, thank you for subscribing, by the way. Please do like, share, subscribe. I just got back from the gym. You can enjoy Baji. And my hair is wet. Because I did take a shower. And whatchamacall? I did my swimming, I took a shower. My hair is wet. But we're ready. We're ready to do this live in right now. Hello. Hello, everybody. Hi, Pumbafo. How are you doing? We might have to change the title of the live. I don't know if we're going to talk about dark energy tonight. It might be more of the quantum mechanics and string theory stuff that we will do. There's definitely, you definitely saw a kitty cat. By the way, this lipstick that I wore the other day that people liked a lot is from Lakme. It is Cushion Matte lipstick. I won't put it on just now. I had it in my pocket because I'm gonna eat the soup and then maybe I'll put some on because people liked that red color lipstick I wore a couple of days ago that people were complimenting. That's this lipstick. It is by Lakme. See, I'm not lying. Lakme Cushion Matte. Hi Tyson, how are you doing? I'm looking at you guys' comments over on this side as well on my laptop. How are you guys doing? Hello, 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 hello. Hello, 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 hello. What's up, girl? Love you. Hi. Hi, Xander. Hi, Tyson. Hi, Ninja Fist. I added a profile picture. Oh, let me see. Can I see your profile picture? I have to really, because it's hard for me to see the tiny little profile pictures. I can't always see who you are or what you look like, but thank you for sharing. So, here is me. I am Baji's mother. Baji is a kitty cat. This channel does show kitty cats as well as my face, teaching physics, astrophysics, cosmology, astronomy. The topic of tonight is going to be more physics, probably more of the quantum mechanics, 20th century stuff, the spooky action at a distance, the Einstein work, unified field theory, string theory, those types of things. So hopefully you enjoy, hopefully you subscribe, because I think it really helps when you come back to the lives and continue with us on the different topics. I want this light on. I want this on. And such. Okay, so spooky action at a distance. Yes, spooky action at a distance is a topic that is of interest, and we kind of mentioned it a little bit last time, and we will review that tonight. This has to do with some of the implications of quantum mechanics that was pointed out actually by Einstein and his students. So we will talk about that again because it is a really interesting topic, and I think it helps people to get a perspective on some of the things in quantum mechanics. Hi, Joe. Joe says, I miss you and missed you. Oh, thank you, Joe. How are you? The last comment got deleted. Oh my goodness, J. Manuel. J. Manuel has sent a gift. Thank you, J. Manuel. Let me like that. Sometimes when the comments go by too fast, I didn't get a chance to like it, but right now I saw it. Thank you, J. Manuel. I really appreciate you. How are you doing? ¿Cómo estás? So which comment got deleted? Let's see. OJ Manuel sent a sun balloon. That was the sun balloon. Oh my gosh, that's right. I see it. I also read it. Oh, thank you, J. Manuel. It's a sun balloon with sunglasses. How interesting. And then the Chaz505 sent 100. Oh, thank you, Chaz, for the gift as well. So let me see what comment I see. Tyson is saying you're so sweet. Thank you. I think I kind of see you, Tyson. Is that a beard? I think I see some black colored hairs and whatnot. So we match. We are same pinch on the hair color. So anyways, thank you so much for being here. Indeed. Always a pleasure to have all of you here. Ninja is saying I love her beauty and her smarts. Well, thank you so much. Have you been doing lives lately? Yes, I go live at least a few times per week. At least a few times per week, I do go live, my darlings. Hi, brah. Or hi, whoop-de-doo is saying brah. Hello, brah to you as well. Your relaxed look is fire. Oh, thank you, Dialectical. I am mostly like this. Sometimes I, you know, get ready a little bit, but mostly this is just my... I went to the gym, took a shower, brushed my hair, and that's it. Didn't do anything else. And put these rings on. And kept mostly the same clothes, but I changed my shirt and my sweatshirt. Because I took I was swimming. I didn't do stuff that causes me to sweat too much. And I have these like Sherpa pants on. I'll show you at some point tonight. They are so warm and so comfy. I'm not getting out of them anytime soon. Can you donate your hair to the women with balding? I did donate my hair a couple of times to the children who need it. So yes, I do that sometimes. How was the workout? It was so good. I walked and then I took the bus. Then I actually missed the bus that I normally take. And I had to Uber for a little distance because even though I was walking, there's a lot of snow on the sidewalks, and around where I live, it's mostly cleared. There's like a snow path where you can walk. You can slip, but generally you can walk. There is a path. But near the gym, it was like every sidewalk is like covered in snow, and they hadn't really made that snow path, and so I had to do a little bit of an Uber to reach the gym. Then I did leg press, so I did some weightlifting, but it was already a little late because I had to do the detour to get to the gym. Then I did my swimming, my usual. That's my reward for coming to the gym, is to swim, because I love swimming and breathing, and it's my meditation. So I did that. Then I took a shower. Then I got dressed in the sauna. Oh no, I also did the hot tub after the swim. Then I took a shower. I assured the girl that works there that I'm going to take a very short shower, so please let me, because the gym is like closing by the time this is happening. I do squats too. Yeah, I'm a big fan of squats and leg press. Those are my favorite weightlifting type of things. So then I did the hot tub for like a very short time. Then I took a shower as quickly as I could, but I like rinsed my hair. Then I grabbed my clothes from the locker and ran into the sauna and like dried off, towel dried and sauna dried, and then put all my clothes on. And then well, I don't drive. I don't have a car at this time. Some send her a $100 super chat. Oh, thank you. So thank you in advance to the person who does that. And also the people who are encouraging that. So yeah, so I did. So then I got out, and then Baji, kitty cats are getting into some trouble here. Then I waited for the bus. Okay, I also crossed the street onto the other side, which is where the bus comes. And then I waited for my bus with the gym janitor. who provides a lot of security at night, actually, because he's this excellent guy who also takes the bus with me. And we have bus friends. We have some other guys that are our friends now that also take the bus. And the bus driver knows me, and he always asks me, or he tells me, your friends are here. Or this time he asked me, where are your friends? And I'm like, which ones? And he said the Indian guy and the Nepali guy, because those guys are always on the bus and the same bus. But yeah, we had to wait sort of off of the sidewalk because sidewalk is covered in snow. But we took the bus, me and the janitor guy. He's from a different country. We never really speak, but we always say hi. And we tell each other if the bus schedule has changed. So I have helped him out once and he's helped me out at least once. So it's really great to have that guy who works at the gym also take the bus with me, because he like makes sure that I get on the bus first and then he gets on, and he's also like waiting for the bus with me at night, which is very reassuring. So thank you to that guy. I don't know what his name is, but we always say hi. Are uthapams expensive in your area? I don't know what that means. Are you talking about like the food? Uthapam? Get his name. I don't think he wants to talk to me. It's just, you know, we're bus friends. We're just bus and gym friends. I think we are exactly the correct duo. I am in meditation mode after the gym, and he doesn't want to talk to me. He's on the phone with his family, probably speaking in a different language. It's perfect. I would never want to ruin that. This is my gym friend and bus friend that is perfectly aligned with me. This is my best friend that is perfectly aligned with me. In fact, the other two guys, the Indian guy, Nepali guy, they're okay. I like the Nepali guy more. He's really friendly and sweet. The other guy, he's a little iffy. You know. So I prefer when they don't talk to me and they're just there and we get on the bus and we don't have to talk. We're good. We're good. Because I do all my talking here with you guys. Tyson is saying, if I was your best friend, I wouldn't waste the opportunity. I like when guys don't talk to me. Too many of them do. I like him because he doesn't talk to me. It's perfect. Like, I wouldn't want him chatting me up while we're waiting for the bus. I'm not looking for romance, my darlings. I'm looking for bus-related security. I don't think you guys understand what a woman wants. A woman wants security without any speaking. Okay, I'm gonna get my soup and eat it while I read your comments. Small talk. I hate small talk. I don't like small talk at all. I only like deep talk. Deep talk. Like, I like full-blown conversations that are huge conversations and deep conversations. All right. 1 second, please. It's the pretty bowl again. But yeah, we're best friends. It's lovely. We're best friends and it's lovely. Indian women are gorgeous. Thank you. He probably knows I'm from India and come from like a more conservative culture where men don't talk to women, you know? He's very respectful. This is exactly what I need in a bus friend. Oh my God, I love that comment. Ari the dog is saying, does quantum mechanics count as small talk given how small the atoms are? That is the only kind of small talk that I would ever prefer. That is the only small talk that I want to be accused of, is quantum mechanics. I love it. I'm going to use that. I love it, Ari. You've made my day with that comment. Pretty much the only small talk that is worth doing is quantum mechanics small talk. You should definitely see the cat wall stuff. Hi, Peter. Thank you. I think Baji went upstairs. I don't see him. I love your hair, says Paula. Thank you. Hi, Mr. Vision. Okay. Baji doing cat things? Yes. Hi, Muhammad Mariam. Apu Karab Kichu Corbin. What do you mean by that? My name is Emma, not Paula. Hi, Emma. Anjas. Hello, Anjas. Mary, can you sing Kuch Kuch Hotai? I can. I certainly can. All right, guys, please give me a moment to eat my soup. Let's see. Can I define time? Time is one of the 4 dimensions in general relativity. Time is relative, so is space. And you can slow down or speed up depending on the gravitational environment, as well as the reference frame. If it's an inertial frame, the speed of the observer. In this universe, time got started when the universe got started at the Big Bang. That is considered t equals 0. This is Progresso. This is beef pot roast. Country vegetables. Progresso. You look like someone in a group of mathletes. Is that like an athlete but mathematics? I look like Chris Pratt. Who is that? Is that an actor? Put my hair up for the eating part. Is that an actor? Thank you for the gifts, guys. Really appreciate it. You look like a spelling bee champion. Oh my goodness. Oh my goodness, hi. Dixon Myers, he's from Argentina. Do you remember him? I don't know if I remember him, but thank you so much for being here. A high noon duo. Hello, high noon duo. How are you? Thank you so much for being here, and thank you to Dixon. What's up? Big fan of your stream. My friend recommended me to your channel. His name is Dixon Myers. He's from Argentina. I plan to go to Argentina soon, hopefully. By the way, are you guys like fans of football and are gonna see the Super Bowl this weekend? War, as in like the World War 1 and 2, or what do you mean? Hello, Craze. Hi, Pumbafo. I'm trying to see you this weekend. Okay. I'll probably go live. Thank you so much for seeing me this weekend. World War 3. I'm a fan of that soup you're eating. Aw. Thanks so much. Can you give him a shout out? He's sitting next to me. Dixon Myers Jr. Hi, Dixon Myers Jr. How are you doing? Hi, Ray Appliance. Hi, Bryce. Hi, Anjas. You guys are chatty. I love it. You know, I think I'm gonna switch the direction because my one light has gone out on this side, and there's more light if I look at you guys in this direction. Less light in the other direction. Is that better? I realized my light is dimmer on this side. That light is gone. The bulb is gone. Ooh, and there's my burgundy curtains that you guys like so much. Hi, High Noon. You should figure that out by staying on the live for a long, long time. My ethnicity is heavily discussed here. Anyway, how are you? What's your channel about? It's about physics, astrophysics, cosmology, and astronomy. And eating soup and kitty cats on my face. You are the sweetest. Oh, thank you. I don't have a cold. I just was swimming. She is a beautiful Indian lady. Oh, thank you, Ninja. Thank you, guys. You guys are sweet. This way, the light is better, but I guess you can't see Baji. You can't see Baji. You just started studying quantum mechanics. Oh, very nice, Bryce. We will all study quantum mechanics tonight. Cosmology is the study of the universe, things like the Big Bang, expansion of the universe, dark energy, dark matter, evolution of the universe. Dora. So that is cosmology. Cosmetology is the study of cosmetics, but not cosmology, okay? Study of the cosmos is cosmology. Thank you, Kensley. Hi, Wild and Fresh. Would you ever date a silver fox? What does that mean? Again, can you clarify? Can we travel in the speed of light? No. We cannot. Only light can travel at the speed of light. I really need a chef, Kenny. A guy with peppery gray hair. You know what you should do? A guy with peppery gray hair is heavily encouraged to do a super chat. Hello, Han John. Hi, Jorge. You need to come home and relax your mind. Do I have kids? I do. They're feline. Kenny is saying something. Hi, Kensley. Do I have human kids? No. Did you guys subscribe? Did you subscribe? By the way, I saw the comment by Soulful, and I want to say thank you. Thank you, Ari. Kaden is asking, do you want to have kids? Why do you ask? Hi, Muzzle Lifestyle. W chat for clicking? What does that mean? It is winter time. I encourage. It is winter time in the northern hemisphere, at least, of both Earth and Mars. I encourage some soup eating, you know? Am I in the United States? Yes. Let's look at the top fans. Number 1 is J. Manuel for doing a gift. Thank you. Thank you, J. Manuel. Number 2 is God Bless America. Number 3 is Anjaz. Number 4 is Af Manute. Number 5 is Caden. Number 6 is Danish Khan. Number 7 is Pumbafo. Number 8 is Dialectical. Yay. Number 9 is Yup. John Bobby. And number 10 is Peter. Oh my goodness. How are you? How are you guys? What is disrespectful again? Hi, Exode. Do you want me to give you my lat and lawn? Hello, Servin. It's been lovely saying hi to everybody. Once I finish, we're gonna study some physics. I don't think my mods are here, except Tyson. Tyson, are you here? Still here? Sorry, it's taking a moment to finish eating. Oh my goodness, Presley. This is soup. Do you mean Andromeda? Thank you, Julian. Hi, Robert. So the Milky Way, we actually covered a paper, a recent research paper. We actually covered a recent research paper that said that the Milky Way galaxy might not actually merge with its neighbor Andromeda, as in there was like a 50% chance of it not merging or merging, right? Because it's 50-50. So basically we were thinking in the past that merger with Andromeda is pretty much guaranteed, but at this time it is not so guaranteed anymore. We think that there's a good chance it might not merge. And that is because of the gravitational effects of other neighboring galaxies. There's the Large Magellanic Cloud, there's other neighboring galaxies in our cluster of galaxies, right? In our local cluster. So all of that is to say that in the local cluster, in our local neighborhood of galaxies, gravitation is still kind of winning. Not kind of, pretty much it is winning. gravitation was allowed to win in some spots of the universe, and that's why and how we have clusters and galaxies and star formation and stars making heavier elements and then dying and spewing the material and making nebula, and that nebula cooling enough to make the next star system, such as our own solar system. So if gravitation were not allowed to win in some spots of the universe, then we wouldn't be here. We're here because of gravitation winning sometimes. And what we find is in the local cluster, gravitation is winning, but when you look at the universe at large, on a larger scale, as in you look at galaxies that are really, really far, far away, then those galaxies are receding. They're going away from us. The distance between us and them is increasing with time because of the universe's expansion. So there's really a couple of things going on. One is gravitation, which brings matter closer together. And that matter could be ordinary matter or dark matter. We know, for example, that dark matter plays a role. We have to verify and confirm exactly how it plays this role because we don't yet understand exactly what dark matter is. But dark matter is something that we find even in our own galaxy. We just don't know exactly what it is. We just know its gravitational effects. Its gravitational effects are very real. But exactly what the nature of it is something we don't understand. Because it's a research topic, it's not done yet, fully fathomed yet. So all this dark matter, ordinary matter, us, because we are made of ordinary matter. Pretty much everything we know in the standard model of particle physics is ordinary matter. But it turns out when you take account of the cosmos and you do some bookkeeping or accounting of the cosmic ingredients, it turns out that out of maybe 25% matter, only 5% is ordinary matter and 20% is dark matter. So dark matter is more than ordinary matter. It's the more dominant cosmic ingredient at this time of the universe, at this stage of the universe, because the universe also changes and evolves from its birth until up to now. It's not the same throughout, okay? Again, if it were the same throughout, then we wouldn't be here. We are a thing at this point, or evolution of the universe. So I was saying earlier that gravitation locally does win. We are in the locality, obviously, of some galaxies, right? We wouldn't be here. This Milky Way galaxy and its neighbors in the local cluster wouldn't be here if there wasn't some clumping of matter and gravitation winning and forming this local cluster and its galaxies and stars and things like that. But overall in the universe, there is this other factor, other thing going on. So I mentioned two things. I've been talking about gravitation so far. The other thing is dark energy, which is the name we give to the effect of expansion, the thing that causes expansion of this universe. And that's also been happening ever since the Big Bang, pretty much. So we get an expanding universe. And we don't see any evidence of contraction, really, like a big, people sometimes talk about the big crunch, where maybe there will be, at some point, the universe kind of contracting. But we don't really see that so far. We see expansion. So what that means is that on a larger scale of the cosmos, because our local cluster is not really the scale of the cosmos, that is the local cluster. You have to get more specific when you talk about cosmology. And you have to get galaxies and, basically data from very far, far away, all these different redshifts, high redshifts away. So those galaxies that are really far away are actually receding. They're moving farther and farther away. And that is because of expansion. And that is confirmed by the Big Bang Theory. But as far as our local cluster gravitation winds, and we may or may not merge with some of these neighboring galaxies in the next few billion years, we thought we would definitely merge with Andromeda. But currently, it looks like that is about a 50-50 chance, as far as I know, based on a paper I read last year, because they accounted for more galaxies and gravitational effects on top of what we had done. Okay. Hello, Sign Sand. Hi, Randy. The kitty cats are upstairs. War and Peace by Tolstoy. I don't think I've read it, but I've heard of it. It's a good book. World War III. I hope there is no World War III. Hi, Will. Hello, everybody. Okay, so that was to answer somebody's question. Any other questions? Somebody asked about war. Twix. Twix is one of my favorite candy. I love dark matter. Hello, Nusrat. How are you doing? What was your question, Exode? I have to dig through these chat messages to see it. Hi, Viral. All right. Let me finish my soup. Yeah, there's a lot of galaxies. Hi, Northern Versus. Okay. What did I miss? What was your question? This is a soup, a beef pot roast. If you have a question, can you do a super chat so I can see it more easily? Thank you, Hula. Okay, so I think what we will do is we will pick it back up from the spooky action stuff that we were talking about. So who can tell me about the quantum properties of particles that we have discussed? So let me share the live as well. We discussed that Einstein discovered the, yes, we did discuss that. And then what are the different quantum properties of a particle? One of them is mass. Who wants to name the others? Northern is saying spin up, spin down. Yep, spin is one of them. Very good. Particles. I'll take that. So charge is one. Very good, guys. Somebody's now mentioning the uncertainty principle, position, momentum, got it. Quarks is a family of particles. We're talking about the properties of all the particles. Mass is one, spin is one. Some others. Name some more, please. Mass, spin, charge, and one more. So I see somebody said quarks, so that is one of the family of particles. So even quarks will have some of these properties. So what are the, okay, let me change the question while you guys still try to answer the first one, which are, what are the properties of particles, all the quantum properties. We have named some already. Mass, charge, spin. Hi, J-Dub. The other question is, what are the particle families? And someone already said quarks. Quarks are one of the particle families. When I say quantum properties, I mean like certain identifiers. Like basically if I told you the mass, the charge, the spin, and something else, you would basically have, and those are the main properties. The one that's missing right now is sort of not as well known, but these are sort of the identifiers. If I told you, so by the way, the fourth property is color. It's something that quarks have. And so, hi, boo-boo. So mass, charge, color, and spin. So if you basically have these four properties, it's not real color, no. It's not like actual real color. If you had these four identifying properties of any given particle, like if I told you four of those things, then you'd be able to tell me which particle it is. It defines that particle's different quantum states, okay? But yeah, some people mention wave-particle duality. Pretty much that's true generally for all the particles, and for, you know, light is one of them as well. And then some people mention quarks. That is the name of one of the particle families. So in quantum mechanics, in particle physics, there are three families of particles, three types of particles, and under each family, there is multiple of that family's members. So quarks is actually quarks are actually one of the families. So what are the other two families? There's two more. So somebody already mentioned quarks. What are the other two families of particles? Mass, charge, color. Leptons! Very good. Mass Mayhem is saying leptons. That is one of the other families. So we said quarks, leptons, and what's the last one? How do you charge your... Okay. Bosons! Absolutely. Abdul Kudus is saying bosons. Bosons is with an S. Dialectical said bosons and leptons. Yes! Absolutely. Absolutely. So the three particle families are leptons, quarks, and bosons. And bosons is with an S. Correct. 43 handle. Thank you so much. 43 handle said boson. Exode said something. Dialectical said bosons, leptons. Very good. Protons are made of quarks and electrons are a type of lepton. So protons and electrons are actually not the same kind of particles. Okay? Protons are actually a composite particle. It's made up of 3 quarks. So quarks exist in composites usually. Proton is a quark composite made up of multiple quarks, 3 quarks. Neutron is also made up of multiple quarks, 3 quarks. Electrons are a completely different family of particle. Electron is a type of lepton. So those are the families of particles that we have mentioned. Leptons, number 1. Quarks, number 2. Bosons, number 3. Quarks, bosons, leptons. Which one has more mass? That's a great question. We have to dig into the particular particles in each of those families because there's multiple particles under each family to there are multiple particles under each family, so we would have to look at each one specifically. Okay, so for example, oh, thank you so much for the gift. Oh my goodness. Hi, Joe Castle. Joe Castle has sent me the cat ears, which are looking very nice on my head indeed. Thank you so much. That really cheers me up. Thank you, Joe Castle. One second. Let me put this over here. Let me move this here. Okay, now I'm done with my soup. So, there are multiple particles under each of the families of particles. And sort of the way some of this is organized is sometimes people call them sort of generations of particles. So for example, under leptons, there are electrons, muons, and taus. These are the different types of leptons, as well as actually the neutrinos are under leptons. Neutrinos are very low mass particles, but there are like 3 flavors of them: electron neutrino, muon neutrino, tau neutrino. So even under the leptons, electrons, muons, and taus have different masses, different lifetimes. I think somebody mentioned lifespan, and that's a good point. Not all of the particles have the same level of stability, and they will decay or have different lifetimes, depending on which one you're talking about. So this is what I mean. Depending on the quantum states, the mass, the charge, the spin, the color, you'll be able to know which exact particle we are mentioning from the families of particles, okay? So for example, the mass is going to be different between the electron and the muon. The electron is going to be lighter. Same thing is, not same thing, but similar thing under the quarks. There are quarks that are heavier, there are quarks that are lighter. Okay, so there's up quarks. Some of the quark names don't have a lot of meaning, but for example, there are up quarks, there are down quarks, there are top quarks, there are bottom quarks, you know, all that kind of stuff. And then somebody asked about the Higgs boson. The Higgs boson is a particle under the boson family. So the Higgs is a boson, and it's one of the bosons. The photon is a boson with no mass, for example, also a boson. So sometimes, you know, when we talk about bosons, the most easiest example to give is really the photon, because the photon is, you know, light particle, the particle that makes up light, as light's particle nature, right? So photons have no mass, they travel at the speed of light, which is also a constant of nature. The speed of light in vacuum is a constant of nature. So let me move that a little bit. So that's one of the bosons. Now there are multiple types of bosons as well. So somebody mentioned the Higgs boson. That is definitely one of the bosons. And then there's also bosons called W and Z bosons. Hi, Kenny. Thank you. You can stay for the live if you'd like. So there's also the W and Z bosons, which are actually the carriers of the weak nuclear force. And do you remember what the weak nuclear force is and who interacts through that? Because we've mentioned it. W boson and Z boson. Yes. W and Z. No, sorry. W boson and, what I'm saying is W and Z bosons. W bosons and Z bosons. Okay, those are two different things. And those were discovered as being the carriers of the weak nuclear force. Because remember, when, so for example, because we have been covering some of the history and the 20th century physics, right? So, exactly, good job. Responsible for radioactive decay. Yes. Mass mayhem, gold star. Very nice. So basically, during Einstein's time, do you remember we talked about this? We talked about the earlier part of the 20th century when we have been given relativity by Einstein. Special theory of relativity was given to us by 1905. So pretty early on in the century. And by the time it's 1915, we already have general theory of relativity. And then we also saw the rapid development of quantum mechanics as a field and some of the bizarre qualities of quantum mechanics, and so on and so forth. And we were mentioning how, because quantum mechanics was bizarre, it motivated Einstein and others to work on a more general theory that can subsume quantum mechanics as well as relativity. Also, of course, they were interested in unifying gravitation and electromagnetism. Really, until about 15, definitely until 1915, they knew about two fundamental forces. They knew about gravitation on the one side and electromagnetism on the other side. They knew about these two fundamental forces. So Einstein realized, like, well, there is nothing that's really unifying those two. And then, along with that, there was the onset of rapid development and as well as a lot of confirmation and success of quantum mechanics. Because if quantum mechanics had just been bizarre with no experimental success, then they would have just shot it down. They would have killed it. But because it had immense experimental success in, for example, explaining the hydrogen atom and, discovering particle after particle, some of these particles that we just now mentioned got slowly discovered, right? Under quantum mechanics'
success. We basically got all of particle physics. So because this was happening, Einstein was very, very motivated to find a unified field theory or a grand unification theory or a theory of everything. Those are all pet names of the same thing. To explain quantum mechanics and relativity, so that he could explain quantum mechanics as a sort of just category of things under this more general theory, because he didn't like some of the bizarre qualities of quantum mechanics. Quantum mechanics is rather weird, especially to the classical physicists, and we'll kind of talk about that in just a moment here as a recap from last time. But basically, the thing was, though, the issue was, I just named a few things and you also named a few things from particle physics knowledge, and not all of that was really known during his time. So we mentioned about weak nuclear force, and actually we also mentioned about strong nuclear force, because the quarks interact through the strong nuclear force, the force that binds together protons and neutrons in the nucleus. So the stuff that keeps the nucleus together in atoms is governed by the strong nuclear force. And then we also mentioned weak nuclear force, something that the neutrinos interact through, and things like radioactive decay, etc., happens through that. Well, those two things were not discovered until much later in the 20th century. And so if you were to come up with a grand unified theory or a unified field theory, you would actually have to know about these things as well before you could successfully have a grand unified theory. So I wanted to mention this now because it's a good time, because we're discussing some of these particles and the carrier forces and the bosons and all this stuff. But just keep in mind that this knowledge was only incompletely known in the first part of the 20th century. They didn't even discover the neutron until I believe 1932. So you can double check that, please. Any of this information you should definitely be double checking on Google. You can read papers, whatever. But basically, they didn't even know about, lots of many more details until later. As things get more and more discovered, or rather, I should say, as more and more things get discovered, the more you have to explain and the more you would have to contain within your unified field theory. So keep this in mind as we go through and discuss quantum mechanics and particle physics. The more we know as part of quantum mechanics and particle physics, the more a grand unified theory candidate would have to explain. And I'm glad we talked about the quantum properties or the quantum states of particles, including, of course, mass, charge, color, and spin. Spin is something that comes up in our spooky action at a distance topic. But those properties of the particles, also we mentioned the particle families and what they interact through. All of this has to fall out of the general theory. All of this is something we get out of quantum mechanics and its developments and particle physics as a consequence. And, some of these are sort of known or found, but there might not be sort of a more overarching theory explaining these things, but these properties are known. So basically, if you came up with a theory that you are claiming is the grand unified theory, it would also have to spit out all of these quantum properties and particles and those forces and all of that stuff that we mentioned, okay? And of course, it would have to unify the four fundamental forces, which are gravitation, electromagnetism, strong nuclear force, and weak nuclear force. Okay, so I wanted to take a little moment here as we are in this particle physics type of mentality to mention about that, okay? Because it is, physics is obviously a lot of different topics, and we have to keep in mind like what these people were, looking for and working on and trying to work on when we are reading from the book Einstein's Cosmos that we've been using here on the lives for a couple of lives here, we've been looking at Einstein's work and some of the developments in the 20th century. And back of your mind, you should try to keep the bigger picture there so that you understand why certain things are done the way they are. Okay? And as you learn, and if you didn't catch everything about particle physics on these lives so far, we certainly will go over a lot of these topics again. So don't worry about that. You know, we often review particle physics basics here. But as we understand and learn about particle physics and the various properties, various particle types, families, this and that, just keep in mind about the bigger picture of what these people might have been trying. So, because sometimes we can dive deep into a specific subtopic of physics, and sometimes we have to zoom out and understand where everything kind of fits. And actually, gaps in that are still very much there, right? It's not everything is not understood and everything is not known. For example, we mentioned, I'll finish my sentence. What I was going to say, gaps exist, but the nice thing is, both the challenge and the sweet part of this is that everything connects with everything. So the more you know, and the more you can find, and the more you can research, the better. But basically, for example, we just mentioned about the particle families. Well, for example, something like dark matter, we don't know yet what the particle nature of it is. Does it fall into one of those three categories? We think not. Okay, so this is where basically having a mindset to kind of sometimes zoom out and understand exactly what's going on is useful, okay, in your overall understanding. Hi, Antonio. Hi, Mass Mayhem. Do I have a degree in physics? I do. I have multiple degrees in physics, but thank you for asking. Hello, Alpha. Hello, Sky Surfer. Thank you, Kenny. Thank you, Sky Surfer. Thank you, user. Thank you, Mr. Vision. Welcome to Turkey. Thank you, Kenny. Hi, Horel Dai. Thank you so much. Hi, Hanjan. Hello, Disneyland. In your opinion, what is the best theory that meshes? That's a great question. So Mass Mayhem is asking, in your opinion, what is the best theory that meshes general relativity and quantum mechanics? So, I don't know. I guess it's superstring theory. If I had to really pick one, I would just go with superstring theory. We have covered some basics of superstring theory on these lives, and we will continue to for sure again. You know, I don't know a ton about quantum gravity, and I'm not sure that some of these efforts, such as quantum gravity, that are being done, it's a current effort, right? So it's actually a goal of mine to learn more about those current efforts, and I can cover those as well. So, partly, I would say, what meshes, the question being, what meshes general relativity and quantum mechanics the best? Partly the answer is I don't know. Because, first of all, I don't know that there is any really good theory right now that does a great job and is testable, right? That is the issue. So I don't know, because I don't know. Yeah. The first answer is I don't know. But I would be very happy to learn more about all of the current efforts that are going on, because, what I say I don't know today could get more research done and published tomorrow. And then it is our duty to kind of understand those things that are coming out, that are being published, that are being researched, and communicate that out to the public. So I'm very much interested in learning about the current efforts. Something that we have covered a lot and I've talked about and we have read from books on and, discussed at length is superstring theory, which is the opinion of many that is the best candidate for the meshing of gravitation and particle physics, So, like, basically the meshing of gravitation with the other non-gravitational fundamental forces. So, superstring theory obviously was motivated by exactly that, to become the grand unified theory, to become the unified field theory. And why I say it's a candidate for the grand unified theory, and I don't call it the grand unified theory. So there is these subtle little terminology which would be good for you to know, all of my friends here, is that we have to say grand unification theory candidate when it's not experimentally verifiable. So there could be a theory, but if it does not have a lot of experimental success, then we cannot really call it the theory or the theory of everything, right? So the superstring theory is a theory of everything candidate. It is considered a pretty strong candidate, actually, as far as I know, anyways, and as far as, of course, the string theorists would like to say, anyways. But the problem with superstring theory is that it is not experimentally testable. And because it's not experimentally testable, we are at a roadblock of not knowing, whether it truly is true or not, whether it truly is the grand unification theory that we seek or not. And really quickly, let me mention why it's not testable. It is because superstring theory, and by the way, I'm saying superstring theory, not just string theory, because I mean, we had to take string theory and we had to make it SUSY, as in supersymmetric string theory. So that super word comes from the SUSY, supersymmetry, okay? So there is, supersymmetry as a topic is also something we need to test and verify, blah, blah, blah. But basically there is, let's say, a more elegant, more beautiful version of particle physics that is required by string theory. So just string theory is not enough for becoming a grand unified theory. We need to have the supersymmetric version of string theory. And I believe that that is when it can actually combat some of the challenges it had in its mathematics to become a candidate grand unification theory. So, yes, keep in mind that not just string theory, but superstring theory it would have to get confirmed. We would have to also find supersymmetry partners. So basically, supersymmetry says something like all the particles have a supersymmetric superpartner. It requires this extra symmetry of nature. In other words, like a lepton will have a slepton. I always thought that was a funny word, but yeah, supersymmetry. Yeah, well, yeah. Supersymmetry, it has not been, yeah, that's what I thought. I think I would have heard if it was found. But let me just say what Susie is, okay? So supersymmetry is love how you can study to be a doctor and still have time to live stream. Hi, Craig. I'll come to your question or comment in just a second. But okay, let me just say what Susie is. So Susie is short for supersymmetry. Okay, so we say Susie, supersymmetry. And I think it's a fun little topic. So let me tell you. Basically, supersymmetry implies and requires that in particle physics, we have all these particles I just mentioned, right? We named some of them together, leptons, quarks, bosons, right? Supersymmetry wants the symmetry of nature to exist that gives each of those particles a supersymmetric superpartner particle. So a lepton is going to have a slepton, and a quark is going to have a squark. So you might have heard of antiparticles. So electrons having an antiparticle called positron. That is old news. That is mundane at this point. We know that's a thing. This is different. This is not about the particles having antiparticle partners, but this is about another type of symmetry, okay? Particles having a supersymmetric superpartner particle, which has to be confirmed. That is the supersymmetry that we are speaking about. And that supersymmetry is also required by superstring theory. So once string theory takes that elegant symmetry into account, we call it superstring theory. And superstring theory is the grand unification theory candidate that we cover on these live streams. That's the one I know about, okay? And that is also considered to be the candidate for grand unification theory. But of course, people are still working on their own unified field theory candidates as well. So I don't want to say that this is the end all be all. We should all keep an eye open and an ear open for new results coming out that could give us the new grand unification theory candidate. Now, issue with superstring theory is, unfortunately, it is not testable. Why is it not testable? Because along with the supersymmetry particles that I mentioned just now, requiring the symmetry that those supersymmetry superpartner particles exist of all these particles that we know about already. On top of that, superstring theory requires extra dimensions. So superstring theory requires, and the key word here is requires, not just gently suggests, but requires extra spatial dimensions. So you know how general theory of relativity has 4 dimensions, including time, the 3 spatial dimensions that we know and love, height, width, what's the other one? Length, X, Y, and Z. So the 3 spatial dimensions plus the time dimension in general theory of relativity is making it 4-dimensional. So general theory of relativity in that sense is conservative in the sense that it doesn't really require any extra dimension or anything that we don't already understand in physical reality. In our physical experiences as human beings, we experience 3 space and 1 time dimension. That is what we see, that is what we know and love. There's nothing really strange about that. And the geometry, the Riemannian geometry, 4D geometry that general theory of relativity utilizes uses the 4 dimensions that we already experience. 1 time dimension and 3 spatial dimensions. Now, superstring theory requires extra spatial dimensions. So superstring theory still has the 1 time dimension, but depending on which version of superstring theory, it requires 9 or 10 extra spatial dimensions. Total spatial dimensions. It requires 6 or 7 extra spatial dimensions. So, because the 3 is already there. So, superstring theory is either 10-dimensional or 11-dimensional, where the 4 is our normal 1 time and 3 spatial dimensions. And then there's these extra curled up tiny dimensions that are required in superstring theory. So once again, superstring theory requires, not gently suggests, but requires either 10 or 11 total dimensions, of which 4 are what we already know. What is all good? General theory of relativity also has those. That's the 1 time dimension and 3 spatial dimensions. But where it's very different in superstring theory is that it requires 6 or 7 extra dimensions that are spatial. 6 or 7 extra spatial dimensions. These are called hidden dimensions or extra dimensions or curled up dimensions or tiny dimensions. And these dimensions are what is suggested we don't experience but are there. Well, whether we experience or not, those extra dimensions are required by superstring theory. As in, superstring theory does not work if those extra dimensions are not there. So you can see how it would be problematic if we never discover these extra dimensions, because it's very strongly required by superstring theory. So for superstring theory to be successful, it needs those extra dimensions. And if we never find the extra dimensions, then it'll always be this question mark of whether those are real or not. Unfortunately, those extra dimensions are very tiny. They're tiny. Some people, the string theorists, call them tiny curled up dimensions, as in they're so tiny and curled up, little baby curled up dimensions, that we don't experience them. We experience the normal, larger dimensions, length, height, width, time, of course. But superstring theory wants and requires these extra spatial dimensions that they're saying are tiny and curled up. And there are good reasonings given as to why these curled up dimensions might exist. For example, we talked about the fish under the lotus leaves in a pond, remember? Where, say for example, if a fish is swimming, this is an analogy, by the way, this is not actual string theory explanation, but an analogy for where maybe you and I have limitations and we don't experience every dimension is the following analogy. Let's say a fish is in a pond swimming, and it pretty much has a 2D life. It's chosen a depth. It's just under some lotus leaves and lotus flowers under the surface of the pond, and it just swims like this, you know, 2-dimensional. So the fish is 2-dimensional. And it never really, I guess it's a fish that doesn't come up for breath, like, for example, turtles do or whales do. You know, whales are very much 3-dimensional in that sense, right? So this fish is just kind of swimming in 2D, okay? For some reason, they don't change their depth, and they certainly don't come up for air. So then this fish is going to think that life is 2D, and it's just never going to know that it could just break onto those lotus leaves that's just there above where it's swimming, and it would open up a whole new dimension, the height dimension, and it could discover the lotus flowers, the leaves, the air, all kinds of things if it could experience that third dimension, but it doesn't. So it only experiences life in 2D, and it only thinks that there are 2 dimensions. So what if we are like that? You and I, we could be like that, where we think that there are 3 spatial dimensions We experience length, width, height. Maybe there are 6 or 7 extra small, tiny, curled up dimensions, but we will just never know because we don't experience them unless some of us do, and I don't know, you know. And maybe we're like that fish who thinks that there's only 3 spatial dimensions when there's actually more. We just don't experience them. So it's a strong case, in that sense, where we don't have to experience everything for it to be real. In this universe, there's actually things that we will never experience, right? The universe is infinite. There's things that are so far away where the light cannot travel to us anymore. So we will never know what is there, right? We will never actually know. But those things exist, right? There are things going on at faraway distances that we cannot reach, but that doesn't mean that those things don't exist. We will never experience those things. So what I'm saying is the extra dimensions of string theory are not the only things that we will never, or so far we never experienced, but could be real, could be very real. There are real things that we don't and may never experience, okay? So this is why I'm the type of person who keeps, I can see the both sides of this situation. I can see all of the sides to this issue. On the one hand, sure, there can be things that we never experience, that we will never experience, that could very much be real, I think. On the other hand, physics is an experimental science. We like to have theories that we can verify and confirm with experiment and with something real that can be anchored in physical reality. So it is always worrisome when your theory has things that cannot be verified or testable. And the problem is the dimensions are so tiny in superstring theory, we cannot, possibly probe those dimensions. Oh gosh, I have like a rash developing on my hand. Look at this, how red it got. Oh gosh, well, I guess I'm having an allergic reaction on my hand. So, I don't know what it is. Okay. So, it's unfortunate, really, because basically superstring theory is saying that there are these tiny extra dimensions that are so tiny. They end up being so tiny that we don't have the technology to probe such tiny dimensions. Our technology would have to be probe those types of tiny lengths, and we cannot currently probe such tiny lengths. And that's not so surprising. The universe at one point was so tiny, right? Probably, like we're thinking, probably when the grand unification theory was true for the universe, where all 4 fundamental forces were, the same, could be unified, the universe is no longer that universe for us. That universe was very tiny and had a very different nature, right? Close to the beginning of the universe, when we think the 4 fundamental forces were the same, that universe and the universe today are 2 very different things. We no longer live in that universe. We couldn't have lived in that universe. And so now it's difficult for us to concoct the same type of situation now to run the experiment and get those same or similar conditions as the beginning of the universe to then verify whether these things are true or not. And this is actually a big issue. This is why they built something like the Large Hadron Collider, partly to try to mimic some of these very extreme conditions. I think even Susie, they want to try, they're trying to find in the collider, I believe. Please do double check, because like these types of things, like one of the big reasons for an extreme experiment like the collider is to try to mimic extreme conditions so that you can test some of these things that we are trying to test about theories that are really good at describing, the beginning of the universe. If you cannot recreate those conditions, then it's going to be really hard. So it's a very difficult job that the superstring theorists have when it comes to verifying their theory, because grand unification would imply conditions like the beginning of our universe. And we haven't had those conditions naturally in quite a while. We're very different now than that. That is why we have 4 fundamental forces and we experience 4 fundamental forces. The universe kind of split up these things pretty much as it evolved. And so I feel like once you try to do the grand unification theory stuff, you quickly also appreciate why there are these various different subfields of physics. Because to really get into the depths of something, sometimes you do have to separate it out and learn about each subtopic. But at the same time, the question of grand unification has always been attractive and lucrative for people to get a hold of. Okay, so that's what's going on. It's not easy. It's not easy. The superstring theory, extra dimensions are not testable, making it a candidate theory, which we cannot call totally done because it's not testable. Okay. So Craig said, love how you can study to be a doctor and still have to. So I do many different projects. And so I appreciate that you are coming to the live and we can do the live together. But I'm actually already a doctor. I'm not studying to be one anymore. But there's always studying even after you become a doctor. Why are Indians so smart? Hello, Cody. Smart from curry. They're smart because they arrange everything. String theory is crazy. String theory is not testable. PhD or medicine? PhD. Also, they said at Congress, hearing that. Currently, it is not possible to test the extra dimensions of string theory that it requires. So a lot of people consider it sort of a waste of time. It's a little bit of a harsh opinion that I don't share, actually. I don't think it's a waste of time. But some people can become exasperated and say that it's not worth funding an effort which can not be tested, which remains the case for superstring theory in the sense that its extra dimensions are not testable. And it requires those extra dimensions, okay? Now, I could also see value in testing out the other parts of superstring theory. Like, for example, if they could find Susie, that would be nice, right? That would be further support. Are you dangerous? You're an ED extraterrestrial. Okay, we are all there is. Accepted. Is removing a skin tag. What's a skin tag again? I'm not sure. Do you smoke meth? Indeed, I do not. I'm not a smoker of anything. I don't smoke at all. It's a lot advances with the Hadron Collider. What? Ben is saying something about the Hadron Collider. Okay. Are you married? No. Hello, James. Do you believe in Jesus Christ? Sure. Why not? We are just layers of knowledge from eventually testing. Do you date gangsters? If you watched Star Trek, I always found the Ferranga race was Indian race. Do you date? MIT is mighty interesting time. You smoke your competition. That is true. I'm a little competitive. What about the new nanotechnology that they say is the ultimate AI? Do you mean like making chips so that quick computation can be done to power AI? Okay, sure. I know that there's efforts to, first of all, manage and store data. AI needs a lot of data. And there's also the hardware requirements for doing things quickly and whatnot with AI. So I think those are the two things, like data centers and chips, right? Or am I missing something? I'm not much of an application person. I like to be very useless and unapplied. I like to be very fundamental, which is why I got a PhD in physics and not applied physics or engineering. Indians are more inclined to philosophy. Maybe that's why they're smart. My friend finished med school and became a doctor. He hates it. I did not go to med school. It costs money to go to med school. But if you do a PhD, they generally pay you in the sciences. Indians are very good when it comes to business. Thank you, Sean Banks. PNW Traveler. Hello. Richard is saying, hey, beautiful. Okay, hi. Question remains, is it even possible? Okay, I got that. Aliens have landed. Okay. What about M theory? M theory is the 11-dimensional version of the superstring theory stuff that I was mentioning. So M theory has one more dimension. Can influence subatomic particles and generate electromagnetic fields. Hi, Ben. Hi, Mr. G, Jonathan. Armyhem. Yes, the Kaluza-Klein theory. So we talked about Kaluza and Klein. Soon after general theory of relativity, Kaluza and Klein actually extended the general theory of relativity to include just one extra dimension, which we often quote as this work, we quote as sort of a foundation for what was to come in superstring theory, because they had already kind of taken the leap and included one extra dimension, the fifth dimension, and then unified electromagnetism with gravitation, which was really, really beautiful and elegant. So then the effort kind of died down, but later on, when string theory was developing, it's not like they didn't have any foundation to go off of. Kaluza and Klein had already done an extension of general theory of relativity to include one more extra dimension, the fifth dimension, and had shown that symmetry led to the unification of electromagnetism and gravitation. So exciting thing like that had already happened by the 1920s. Okay, whereas superstring theory, if I remember correctly, didn't really develop much more until the 1960s, and there was sort of a long break before it picked back up pretty much in the 20th century. And Einstein, tried for the last few decades of his life to unify the fundamental forces and to come up with a grand unified theory, but also he lacked the information that you would need to really unify everything, because if you didn't even have two of the four fundamental forces, then how could you unify everything. So he was very much ahead of his time. He was like, he was always trying and he never stopped. He was always looking forward, looking ahead to, accomplish the next thing. But sometimes what holds you back is a lack of information about, the things that are discovered. So, oh my gosh, Acacio! Acacio has done a super chat. Thank you so much, Acacio59. My friend, Acacio, I haven't seen you in forever. Where have you been? Acacio, my friend, ¿cómo estás? Muchas gracias. How are you? Acacio is from the DR, Dominican Republic. And I think he lives in New York. And he has been a long, a long time supporter of this channel, Baji and Physics, of which I am but one of the hosts. The other hosts are all cats, my kids. But Acacio, thank you so much for the 20. Very much appreciate you guys. And also I appreciate your help, everybody, with my super chat goal to keep the channel running. It helps a lot when you support me here like that. So let me keep going here on the comments. So anyway, I hear forces, thought she meant sources. Oh, no, forces. So yeah, the 4 fundamental forces, I mean, you guys know already, but gravitation, electromagnetism, strong nuclear force, weak nuclear force. But 2 of those, strong and weak nuclear force, we didn't know about during Einstein's lifetime. And also remember that the 20th century, so this is something we can talk about in more detail next time. Probably this time I will just focus on the physics part. But basically the 20th century also had 2 wars, right? 2 world wars. And so those 2 wars also very much influenced the physics and the type of work that got done. During the wars, or before the wars, during the wars, whatever. And so it really did derail some of the efforts of some of these scientists that had been otherwise focused, and really, changed the landscape of what got done. And then after the wars, after some time, pretty much the string theory effort kind of picked back up. And at first, the iteration of string theory that we had was something with a lot of holes, with a lot of issues, and it was really wrong. But once they incorporated supersymmetry into string theory and called it, of course, now superstring theory, then it got better. So just know that everything is sort of, iterative. Like you have to build on something. It's okay if at some point your work is kind of wrong. All that means is you have to update it, but generally they are all working off of something and there is a foundation. And so just remember, general theory of relativity is the foundation for Kaluza and Klein. Kaluza and Klein gave us the 5th dimension and it unified 2 of the fundamental forces. Then there was a big break and we got superstring theory later on, 1960s and later. And then instead of 1 extra dimension, they wanted 6 or 7 more extra dimensions. And that's how they unified the 4 fundamental forces, because now there's like 4 fundamental forces. And even then, because it's not testable, it remains sort of a mystery as to whether it's really right or not, But it's always good, take the leap, do the work, and the next work will depend on that, and the next, and the next, and the next. And even I started with general theory of relativity, but really general theory of relativity, of course, is based on special theory of relativity and Newtonian gravitation. So the fact that Newtonian gravitation was sort of, had some issues, but of course it existed. It was very successful in giving us an approximately correct answer. with regard to laws of gravitation, motion, all that stuff. So Einstein took that and improved it. He also took his own work, special theory of relativity, and generalized it to also account for and explain gravity. So pretty much it's important to keep building on top of the stuff that you know already, okay? That's exactly what people have done. Thank you, everybody, for all your support. Oh, somebody, thank you, user VF. Do I accept, somebody asked, Mortal 23, do you accept that you will never have all the answers to the existence of the universe, even if you lived forever? Yes, I hope so. Why would I want to know everything? Then there's nothing more to research. I certainly hope that I won't know everything about everything. That would be very boring. Even in a job, once I know how everything works, I lose all interest and have to change the job. It's very difficult to be bored. We're limited to the... okay, I was quickly looking at your comments. Some of these are really nice, by the way. Thank you so much. You guys are funny. Lovely auto rays. Thank you so much for your comment. Love you're talking about string theory. Other streamers are like, hey, I'm out here. Oh, well, both are fine. Thank you, Kenny. You can play this type of live while you're sleeping. It's actually a sleep ASMR live. Okay, so somebody 37 dimension Hilbert space, which represents 37 independent. Very nice. Thank you, Ben. We can also have fifth dimension. The moment the fifth dimension enters the picture, the researchers proposed that dark matter could be made of particles called fermions that live in a fifth dimension rather than our own. Really? I have to read about that. Can you send me the paper as a comment on one of my videos? That's fantastic. Honestly, if dark matter is just something in the fifth dimension, then I'll be so happy. That's not so bad. I for one, see, some people have a real problem with the extra dimensions, but I, for one, I don't have a problem with the extra dimensions. I have no issues accepting that maybe there are dimensions that I don't experience on the day-to-day, that is. Sometimes if I tried really hard, maybe I could experience it. Or maybe if I didn't try at all, it could just be one of those like sixth sense kind of thing. But if dark matter is just regular stuff in a different dimension, I will be so happy, honestly. Hi, James Lacosta. Can I explain QFT? QFT was probably my weakest subject in grad school. Ghost purge. What is that? Can we get 100 likes, please? Is Hawking radiation dangerous? I would say so. Are you talking about black holes having a temperature and a radiation? Then no, it's fine. Black holes are not really that bad. We'll be fine, okay? The name of our galaxy is Milky Way. Richard asked what's the name of our galaxy. That's a nice question. It's called Milky Way. Sometimes it is just called galaxy with a capital G, and that is to imply that we're talking about our galaxy. Sometimes it's also called our galaxy. Okay? I do want to go to Chile. Oh my goodness, Northern Versus is saying, did you know astronomical is perched on a mountain? Yes. I do want to go to that Chile experiment. If you ever decide to visit, I'd love to tag along. I'll carry your luggage. I'm actually a very light traveler, but if you want to come along, I do want to actually go to Chile. Let's do it. I wouldn't mind. I think it's a little maybe dangerous there, so I wouldn't mind some company. Do I like fish sticks in the air fryer? I don't have an air fryer, nor do I cook very much. But if someone makes it, I'm sure I would eat it because I'm a very flexible eater of things. Given that I don't cook much myself, I'll eat what somebody has to make and give me, please. In fact, that's how I survive, is when people feed me. Robert De Santes. Hello. I enjoy your intellectualism and wonderment. If you could provide contemporary method of ghost purge, and I'm a 1964 baby. Oh. I don't know what ghost purge is, but 1964. That's a nice year. Zoro is saying time is a measurement of space. Therefore, degrees need to be calibrated to like time. Okay. 100 years ago. What did we know? Hi, D8. Have a good night, says Zaro. Okay, sorry I'm not keeping up with the comments very well. Hi, Mohit. Hi, Sean Banks. Progresso. Ben has... I'm gonna look at the paper that Ben is sending. Let's see. Thank you, Ocasio. Once again. So,
Thank you guys for all your comments. Let's see. Oh, I love it. I see the paper that Ben sent. Becky Ferreira. Let me read this for you guys. Scientists have proposed a new particle that is a portal to a fifth dimension. Hi, Geodirt. Scientists want to search for a hypothetical particle that can act as a portal to a warped fifth dimension that mediates the cosmic realms of light and dark. You would be forgiven for assuming that sentence is a science fiction synopsis, but it is actually the mind-boggling upshot of a recent study that seeks to eliminate some of the most persistent enigmas in science. Okay, well, this is the article. It's not the paper. Let's see, where's the paper? European Physical Journal C. Let's click on that. Let's reach 100 likes. Yes, please. That would be nice. We are now looking up this paper that Ben mentioned that is related to our topic here tonight. A warped scalar portal to fermionic dark matter. Perfect. So we will read the abstract here. Oh, they mentioned Kaluza-Klein. Oh, that makes me happy. They're mentioning Kaluza-Klein. We have talked about Kaluza-Klein a lot here. They mentioned Kaluza-Klein, guys. What we talk about in these live streams are getting quoted in real research papers, guys. They mentioned Kaluza-Klein. Thank you, Mass Mayhem. Okay, so once again, this is the European Physical Journal C. Thank you, Ben, for sharing. I love it. A warped scalar portal to fermionic dark matter. So let's look at the abstract. We argue that extensions of the standard model with a warped extra dimension together with a new Z2 odd scalar singlet, provide a natural explanation not only for the hierarchy problem, but also for the nature of fermionic bulk masses and the observed dark matter relic abundance. Kaluza and Klein. Kaluza has a Z in it, okay? In particular, the Kaluza-Klein, so K-A-L-U-Z-A, Kaluza-Klein, you got it. In particular, the Kaluza-Klein excitations of the new scalar particle, which is required to naturally obtain fermion bulk masses through Yukawa-like interactions, can be the leading portal to any fermion propagating into the bulk of the extra dimension and playing the role of dark matter. Moreover, such scalar excitations will necessarily mix with the Higgs boson. Oh, good! If something mixes with the Higgs boson, what does it do? What does it have? Quiz question. Okay. Moreover, such scalar excitations will necessarily mix with the Higgs boson, leading to modifications of the Higgs couplings and branching ratios and allowing the Higgs to mediate the co-annihilation of the fermionic dark matter. We study these effects and explore the viability of fermionic dark matter in the presence of these new heavy scalar mediators, both in the usual freeze-out scenario and in the case where the freeze-out happens during an early period of matter domination. So a couple of different stages of evolution of the universe. So fermionic dark matter would mean that instead of dark matter being a completely different other particle, exotic particle that we have never met yet, it could be something sort of familiar, but requires these very specific situations happening, like what they're mentioning here, the warped extra dimension together with Z2 odd scalar singlet, some Kaluza-Klein excitations of the new scalar particle, all these things, if that happened. So this is a nice little take of that. Fermionic dark matter. Instead of exotic particles, this theory proposes that regular fermions can slip into this fifth dimension, becoming... Yes! Oh, that's a great explanation by Ben. This theory proposes that regular fermions can slip into this fifth dimension, becoming invisible to our detectors, but still exerting gravitation. Kaluza-Klein failed to predict the mass and charge of the particles, though. Okay. Hi, Adam. Isn't this cool, though? Isn't this so cool? Oh my gosh. Oh wait, I forgot to tell you guys, please like and subscribe. I'm saying now. Can we get 7,000 likes and subscribes? Fermions are subatomic particles with half-integer spin that constitute all ordinary matter, including quarks and leptons. Yes. Keep up the good work, Ben. I love it. I love it. I love it. I'm gonna share the live. Hi, Dialectical. I'm gonna change the name of the live as well. We are live. I forgot to share it. Fermionic dark matter! I love reading a paper like that. The study adds, I'm going to go back to the article here. The study adds that the presence of new physics can explain these fundamental mysteries by presenting a model of the universe with a fifth dimension that can be traversed by particles. So I'll remind you that the fifth dimension was already something that Kaluza and Klein had proposed back in like 1921 or something, very early on. And it intrigued Einstein. Now, Einstein was worried at that time that, you know, if something depends on a fifth dimension and you never find the fifth dimension, then that's worrisome. But it was very intriguing then, and I think it's still intriguing now in the sense that maybe if that fifth dimension is there, it can kind of solve some of these problems. So anyway, The study was authored by Javier, Castellano, and Matthias Neubert, theoretical physicists at the Prisma Plus Cluster of Excellence at Johannes Gutenberg University Mainz, and Adrian Carmona at Athenia 3i Fellow at the Department of Theoretical Physics and the Cosmos at the University of Granada. Oh, thank you. Thank you, guys. Thank you. We have been working on a similar topic for quite some time. We will bring the phone a bit closer. How about that? Because I can't read your comments very easily here. My Music Gen X. Hi. How are you? Okay. Dark matter. Yes, please do subscribe. Thank you. Snapshot sniper. Okay. All right. So we have been working on a similar topic for quite some time. Our initial motivation was to explain the possible origin of fermion masses in theories with a warped extra dimension. Very nice. They would not be the first to propose a warped or curled up or tiny little extra fifth dimension at all. The fifth dimension has been proposed as early as the 1900s, literally over 100 years ago, you know. So aloha. Hi, Maze. Hi, JG. DJ, what was your question? How old am I? That's not very interesting. Okay, so then we knew that the masses of these constituents had some special features which were crying out for an explanation. Please do like, share, and subscribe, guys, if you're joining. We are now talking about fermionic dark matter, which is making me very happy. The researchers are part of a long scientific tradition that questions whether the 4 dimensions that humans can comprehend, 3D, space, and time, are really all the universe has to offer. This line of research has produced 5-dimensional field equations that express the implications an extra dimension would have on the universe and reality itself. Yay! I'm so glad that what we were talking about earlier in the live is coming together so nicely with this paper. So thank you so much indeed. It's the fermionic. While researching, so of course, you know, this is a theory paper, so they'd have to like confirm it and stuff like that. But still, it's interesting. Very interesting and exciting. So while researching these equations, Spain, yes, Spain and Germany, right, are the schools that we mentioned. While researching these equations in relation to fermion masses, the team sketched out the existence of a new scalar field associated with a speculative particle that is roughly similar to the Higgs field associated with the famous Higgs boson particle. We found that the new scalar field had an interesting, non-trivial behavior. So if there's a new scalar field, they'd have to like find that. You know. Hi, Julian. Hi, Nausat. How are you? So
they found some new scalar field. We found that the new scalar field had an interesting, non-trivial behavior along the extra dimension. Since this new particle has very similar quantum properties as the Higgs boson, it was very natural to assume that the two particles should mix with each other, meaning that their quantum mechanical wave functions are intertwined. So maybe we'd have to find a new scalar field and not necessarily a new type of particle for dark matter, but a new scalar field. There's still some new things to find though. It's a theory paper, you know what I mean? As they probed this hypothesis, the physicists realized that the heavy particle could offer a unique window into dark matter because it would be able to mediate a new force connecting dark matter and its more familiar visible counterpart, which takes the form of stars, planets, and everything else we can detect with traditional light-based astronomy, because it would be able to mediate a new force connecting dark matter and its more famous visible counterpart. Yes. If this heavy particle exists, it would necessarily connect the visible matter that we know and that we have studied in detail with the constituents of the dark matter, assuming that dark matter is composed out of fundamental fermions which live in the extra dimension, but they would need that heavy scalar field particle. Okay. Yeah. So it's interesting because here what they'd have to discover is sort of a Higgs-like particle that would allow the fermions to slip into the fifth dimension and become dark matter. So it's not really the nature of dark matter, as in the dark matter particle being something else, but this other scalar field, which would have to be still discovered to confirm about this theory. Wow. Wow. This is not a far-fetched idea, since we know that ordinary matter is made of fermions, and that if this extra dimension exists, so you need an extra dimension and you need a new scalar field. The extra dimension is not so crazy anymore because, well, others have thought about that and others have had success with it in the sense of the, theoretical success with it, theoretically unifying things and finding symmetries that are brought about by the fifth dimension. But of course, still not proven experimentally about whether that fifth dimension is there or not. But they're not the first ones to think about the fifth dimension. So you need the fifth dimension and you need that new scalar field. But basically, they don't look so crazy talking about the fifth dimension because Kaluza and Klein did that like over 100 years ago. So it's kind of cool. Okay, models of... I love this sentence. This is not a far-fetched idea, since we know that ordinary matter is made of fermions and that if this extra dimension exists, they will very likely propagate into it. Models of the hypothetical particle did not conflict with real observational evidence of dark matter abundance in the universe. That's cool. Because if this model of this particle conflicts with what we actually see in the real life of the dark matter abundance, then that would be a problem. This general agreement with empirical evidence, along with the hefty mathematical work in the study, demonstrates that the particle could be a possible new messenger to the dark sector. Oh my God. Can you imagine how encouraging this would be to superstring theorists? Because those people are crying, because they're shot down, usually due to not being able to test the extra dimensions. But if you can find a fifth dimension somehow, or if the fifth dimension is somehow likely because of everything else kind of checking out, then that would be euphoric to the superstring theorists. No joke. They would love that. It's kind of like finding neutrons. Am I saying it right? Yeah, it's kind of like finding the pulsars, which gave hope, which is neutron stars. When neutron stars were found, it gave hope to people that black holes might be real. If the fifth dimension is found, or if there's enough evidence to support a fifth dimension, that would, be so encouraging that there might be like more than five dimensions. There could be all those extra dimensions that superstring theory requires. They would love that. Therefore, confirming the existence of such a new scalar particle will open an exciting path towards the possible discovery of dark matter. Oh my goodness! That's so exciting. This will give us, in particular, very useful information about the possible mass range of dark matter and its interactions with the particles we know nowadays. Now that scientists have a lead on this hypothetical particle and its fifth dimension, they have to actually look for it. The Higgs boson was eventually spotted. As we know, we did discover the Higgs boson in 2012, so it's very much a real thing. But it wasn't easy to discover it, right? It's never easy. Takes a lot of data collection and statistics to say that you've discovered something, right? So anyway, now that they have this, the Higgs boson was eventually spotted by the Large Hadron Collider in Switzerland in 2012, an achievement that earned the Nobel Prize in Physics. However, the LHC would not be equipped to search for the particle proposed in the new paper, as it would be too heavy to be generated in any current facility. See, it would have been nice if this was sort of like if this was like the Higgs, but they did mention in the abstract of the paper, this is a new scalar field, as in it's not the Higgs. So whenever you need like a new thing, then of course that has a lot of overhead, because then you have to like discover the new thing. And if that new thing is too heavy or too extreme, then it's even more difficult to discover that thing. Okay, that's the issue. Though the particle might be detectable for a new generation of proposed colliders, more colliders, guys, such as the International Linear Collider, the Compact Linear Collider, and the Future Circular Collider, the researchers said that due to its large mass, the prospects for such a direct discovery seem very challenging, even at the highest energies discussed for such a machine of 100 TeV, center of momentum. They didn't say center of momentum, they should have. Even so, the researchers believe that the particle could be detected more indirectly, such as through observing gravitational waves, which are ripples in space-time. Really? Can they get it through that? I don't know. Another possibility, which we did not explore yet, is that this new particle could play an important role in the cosmological history of the universe, of course, and might produce gravitational waves that can be searched for with future gravitational wave detectors. Oh my god. Oh my god. That's incredible. That is incredible. Future studies of dark matter could also help to constrain the odds of the particle's existence. So the team is optimistic that their fifth dimensional concept will develop alongside advances in particle physics and cosmology. Beyond its implications for understanding dark matter, the particle, if it exists, could shed light on long-standing scientific dilemmas such as the flavor puzzle or the hierarchy problem, while also opening a new window into the early universe. Some progress in understanding dark matter is always welcome. It is one of the top mysteries of the universe. One could study the potential role played by the new scalar particle in stabilizing the extra dimension. This could also eventually lead to an interesting cosmological history of the universe and might lead to the production of gravitational waves. This is an interesting line of research which we plan to follow in the months ahead. One could also try to find new ways of probing this particle at future hadron colliders. As you can see, there are really plenty of things one can think of. There is! Oh, I'm so happy. I am so happy. Thank you, universe. Anything that gives us new ideas for dark matter is always... I am so happy that they talked about they're citing Kaluza-Klein. We've been talking about Kaluza-Klein. See, this is why we must understand the 20th century physics. It's all very relevant, even in today's exact work and current research. Yeah, Ben linked the paper. I'll give you the title of the paper so that you can look it up yourself, because the link is too long to put it in the chat. It's in the European Physical Journal C, which is really nice. It's not all the time that we see a European Physical Journal paper. Oh, you know what? I'll link it in the description, of course. Hi, C. Owens. You like my eyebrows? Okay, thank you. Almost had 7,000 subscribers. Oh, thank you, Wild and Fresh. Really? Oh, thank you so much. Thank you for subscribing, guys. Hi, C. Owens. C. Owens, okay. Hi, Sandeep. Hi, Adam. Thank you. Brush my teeth? Okay, yeah, I plan to. Would you travel to space? But I don't know a lot about physics. And money. We only experience 3 spatial dimensions and 1 time dimension, but we were talking about how maybe there are more dimensions than we experience, and that would be helpful for some of these mysteries. It's theorized that there could be more dimensions than what we experience, okay? Hi, Trucker. Mississippi. I've been on the Mississippi River, but I don't think I've been in the state of Mississippi. I've been in New Orleans, Louisiana, NOLA, and I took a cruise on the Mississippi River. Thank you for subscribing, guys. I appreciate it. I'm gonna change and update the name of this live and the details and description, and include the link of this paper. Please do like, share, and subscribe. Good night, guys. Yeah, we can say good night. I'll hang out for a few more minutes. Thank you for hanging out. You can say goodnight in the chat if you would like. Thanks for liking and subscribing. I will work on the details page now and keep on going. Hang out for we need more money for research of the fermions in fifth dimension. We do. Thank you for helping with our super chat goals, guys. Thank you so much. And you can rewind as well if you want to catch the whole live. Okay. Let me edit the details. I'll put the link of the paper in the details as well, Northern versus. Let me know what you think of the paper if you see it later on and read it through, and you can leave me a comment. We can discuss it further in the comments, okay? So it doesn't have to be over. Thank you. Yeah, there's a paper that we discussed. I loved it. Ben shared it. It's been great. Kaluza-Klein. Fifth dimension. Thank you, Northern Versus. Thank you, Ben. Thank you, Adam. Aww. You guys are so nice and supportive. Dark matter study with me. Kaluza-Klein excitations of the new scalar particle. That's kind of like the Higgs, but not really. Fifth dimension. Fermion slipping into the fifth dimension. If that's what dark matter is, I'll be so happy. You know, there was one time when I read that dark matter could also be sort of like this parallel universe business. And I didn't like that explanation. If dark matter needs another universe, I don't like it. But if dark matter is just fermions slipping into a fifth dimension because of some new scalar field that we still have to find, I'm fine with it. I'm fine with it. Oh, it's so exciting. That is so exciting, guys. I'm so happy. Abstract. I'll paste the abstract as well. Ben, what's the Z2 odd scalar again? Oh, that's the
That's the scalar field. We argue that extensions of the standard model with a warped extra dimension. So we argue that extensions of the standard model. So this still requires an extension of the standard model because it requires that new scalar field. Basically requires like another Higgs-like discovery, which is not trivial. So it's definitely BSM. It's definitely beyond standard model theory paper. You know what I mean? It's not a current known standard model thing, which, I mean, that's probably gonna always be the case. It's not gonna be that we have an answer from the current standard model. That would probably be a little tough. But we argue that extensions of the standard model with a warped extra dimension. So extend the standard model, get a fifth dimension together with a new Z2 odd scalar singlet, so a new scalar field, provide a natural explanation not only for the hierarchy problem, but also for the nature of fermion bulk masses and the observed dark matter relic abundance. In particular, the Kaluza-Klein excitations of the new scalar particle, which is required to naturally obtain fermion bulk masses through Yukawa-like interactions, can be the leading portal to any fermion propagating into the bulk of the extra dimension and playing the role of dark matter. So by the way, this Yukawa-like interactions, I looked it up. Steven! Steven, thank you. Yukawa-like interactions are a type of interaction in quantum field theory that describe the coupling between a scalar or a pseudoscalar field and a fermion field. So the scalar that we've been talking about, like, for example, the Higgs, but this would be a new scalar. So typically representing the exchange of a massive mediator, like mesons, between nucleons. These interactions are characterized by a short-range potential, which decreases exponential with distance. So, strong nuclear force type of thing. So, proposed by Yukawa in 1935 to model the strong nuclear force, where the exchange of massive pions binds protons and neutrons together. Unlike the long-range 1/r Coulomb potential of electromagnetism, the Yukawa potential is short-range due to the e to the minus mr factor. So it's like an e to the minus mr over r, okay? Meaning that the force falls off rapidly, essentially screening the interaction over distances larger than the inverse mass of the mediators. The strong nuclear force is very short range, so that makes sense. The Coulomb force, like the electromagnetic force, is long range, whereas the strong nuclear force, very short range, obviously, right? The nucleus is very short range. I wonder if I'm allergic to like my rings, like my skin is getting redder in spots where I don't even know what's happening to me. Or if I touch, apparently I'm just like allergic today. I do need to take my Zyrtec. In modern particle physics, Yukawa couplings describe how fermions, like quarks and leptons, acquire mass
by interacting with the Higgs field. So this Yukawa coupling is important because it's because of that interaction that we would have, we get mass, for example, from the Higgs boson, coupling with the Higgs. Hi, Mr. Drew. I've been here. You should show your love to my other videos as well. So once again, this is super important, this Yukawa-like interaction, because it describes how fermions get their mass. These interactions are generally attractive and proportional to the fermion's mass and whatnot. Okay, so that's what that Yukawa thing is, all right? So like some interaction with a scalar field, that wouldn't even be, see, the strength of this paper is they're kind of proposing things that people have heard about already. It's not super shocking. Like, okay, look at this. Extensions of the standard model. Standard model has already been extended by many papers, so no one's shocked by that. With a warped extra dimension. One extra dimension is nothing compared to like 6 or 7 extra dimensions that string theory already requires. So again, nothing. In fact, one extra dimension was suggested by Kaluza-Klein over 100 years ago. So amazing. Together with a new Z2 odd scalar singlet. Okay, fine. A new scalar, but whatever. It's all right. Provide a natural explanation, not only for the hierarchy. Okay, whatever. Blah, blah, blah. Then, look at this. Fermion bulk masses and the fermions are things that we know and love. We're made of fermions. So to say that the fermions might be responsible for dark matter, amazing, right? That's freaking amazing. In particular, the Kaluza-Klein. See, Kaluza-Klein we know and love for over 100 years. So if you put Kaluza-Klein in the abstract, clap, 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 clap. Imagine apply this to an AI. Are you talking about me? I do actually work on AI. Is that what you're saying? Okay. Kaluza-Klein excitations of the new scalar particle. So it's a little sneaky new scalar particle, as in we have to discover this new scalar particle, but doesn't sound so bad. A new scalar particle doesn't sound so bad, which is required to naturally obtain fermion bulk masses through the Yukawa-like interactions. Again, we know and love. Yukawa-like interactions are not so bad. Yukawa, we get it. Because of Yukawa, we have mass. So again, they're leveraging what we know already, which is very nice. It's very smart, to be honest. Can be the leading portal to any fermion propagating any fermion. Guess what we love a lot is fermions. So then any fermion, it gives so much hope, right? It's a hope-inducing paper. It gives so much hope. Any fermion propagating into the bulk of the extra dimension and playing the role of dark matter. Amazing. Who is the PI of this? The way they wrote that sentence, Adrian Carmona is the corresponding author. Javier, Castellano, and Matthias. Oh my God, guys. Where is this Adrian? Who is this Adrian? Z2 odd scalar. Wait. I'm in love. Love will find a way. Adrian Carmona is CAFPE. Oh my God, they're in Spain. They're in Spain. No. I must visit Spain. Universidad de Granada. This is in Granada, Spain. No. Hi, Silas. Hi, Princess Tiara. Your skin looks extra beautiful tonight. What's your skincare routine? I go swimming. Whenever I swim, hot tub, shower, and sauna, my face just transcends with the thanks to the universe and thank you, God, which I really do mean. We need to go Spain. We need to go to Spain and learn. Yes, I need to go to Spain, visit this university, and talk to them, talk their ear off about this. Castellano. Uh-huh. My skincare routine is swimming. Hi, anxiety. Hi, Rowdy. Oh, you can keep the live going on your phone and sleep. Close your eyes. I've done that before. I have anxiety too. I have anxiety as well. Sometimes I sleep with a thing on. I also have a sound machine. Anyways, but we must go to Spain and talk to these people about fermionic dark matter. Fermionic dark matter. Low-key, you have really nice eyebrows. Why not high-key? I was gonna say the hairs are also related to swimming, except that I put my hair in a swim cap so it doesn't get ruined by the chlorine. Touché! मुझे आज तक किसी लड़का का प्यार नहीं मिला. Hello, Chibil. मुझे आज तक किसी लड़की का प्यार नहीं मिला. Okay. That's not true. Hello, Princess Tiara. Hello, Stamin. Hi, Key. You're beautiful. Oh, thank you. I need to go to sleep and dream about fermions. Correct. Thank you, ghosts. Can you believe this? It's so cool. It's so cool. I love it. I love it. I'm going to Google the author. Universidad Granada. I'm Googling the author. I found his office hours. Let's go to Granada, guys. Let's go to Granada and do a live. What face moisturizer do I use? Great question. I have it right here with me. Vaseline Cocoa Radiant. This is my downstairs lotion. Excuse me, please. It's very low. Okay, it's not working right now, but downstairs I have this Vaseline. This is what I'll do. I'll take the help of gravity and go like this. See? and it'll trickle down. It will trickle. It will. So downstairs I have this. Upstairs I have a Nivea lotion in a blue container. It's blue. Nivea body lotion, nourishing body lotion in a blue container is what I put all over my face as well. And I use water to clean my face when I shower. Vámonos para España chica. Okay. Let's go to Granada. Let's go to Granada. I'm so happy right now. Thank you, Princess Tiara, for your kind comments, my love. Thank you. It's rather empty, yes. I'm putting on lotion right now. Hi, Silas. Is it really gone? Completely? There is a little bit left. It's done, right? Okay, back to my details page. Exciting paper discussed today. A warped scalar portal to fermionic dark matter. A warped scalar portal to fermionic dark matter. Adrian Carmona. I will put the other names there. Thank you for the gift. Thank you, Cools, Mexman. Thank you. Thank you, Cools, Mexman, for sending the happy poop. Thank you so much. Appreciate you. Thank you, Mass Mayhem. I'm updating the details page, and I hope I see you next time. We will continue with these types of live streams where we cover physics, astronomy, astrophysics, and cosmology with my face and kitty cats. Thank you so much, and see you next time. Hi, Andre. Thank you, Steven. Steven has done a gift as well. Thank you. Thank you all. Cools did a gift. Steven did a gift. Let me look at the top vans real quick. One second. Hi, Sautela Halku. Please close the stream. I can't handle. Oh, thank you. I seen the OR code too. Okay, top fans are number one, Acasio. Acasio did a super chat. Thank you, Acacio, for helping me with my super chat goal. Anybody that helps me with my super chat goal is always much appreciated. Thank you so much. Number 2 is Joe Castle. Number 3 is J. Manuel. Number 4 is Wild and Fresh. Number 5 is Ari, the dog. Number 6 is Steven Sky Reading. And number 7 is Mass Mayhem. Thank you, Mass. Number 8 is Dialectical. And number 9 is Ben Abraham. Thank you, Ben. Number 10 is Mr. Vision. Number 11 is Joe Dirt. Need to go in for some coffee. Good morning. Good morning to you too, Ben. Thank you and see you next time. Really appreciate it. Really appreciate all your help. Steven! Good job. Sanjeev is saying, hello, daughter. How are you? How are you? I'm good. Thank you, guys. You guys are so... Are you from India? Hi, Becky. Hi, Becky. Hi, Loyal. Loyal is saying hello from Scotland. Welcome to Scotland. I love Scotland. I've been. It's very beautiful. Hi, Grace. Oh, we just touched 7,000 subscribers, really. Thank you so much, guys. Please do subscribe. Welcome to Bangladesh. Hi, Adam. Glasgow. I have not been to Glasgow, but I've been to Edinburgh. Welcome to New York. Okay. Thanks for subscribing, guys. If you're just joining, you should rewind so you can see the full live. It's been a very exciting discussion today. Are you from Birmingham? Welcome to Cleveland. Hi, Grace. Grace, how are you? Grace, are you that Grace who was here earlier? Grace, are you the person that we did the sandwich for? I think there was a Grace. Oh, gosh, did you hear that? I cracked. My arm cracked. I'm waiting for Grace to say if she's the Grace. I went into silver? What does that mean?
Need a break and stretches and workouts. I did work out today before this. Magical. Thank you, Northern. B, A plus B. Ahesta, ahesta. No. Hi, Shake. Original, I am original. खूबसूरत से बोली वाली सी. भोली वाली? भोली? भोली भाली, you mean? निकी बहुत प्यारे हैं. Good night, Ben. Good night, everybody. We will see you again soon. I have to go to bed. Oh, I woke you up. I'm sorry. मेरा तो दिल आ गया आप पर. Okay. I'm sorry, Wild and Fresh. Sorry. Go back to sleep. Hi, whoop-de-doo. It is the same live, yes. I gotta go to bed now. I gotta go to bed. I hope you guys had fun. I will see you next time. Thank you so much. I need to take some allergy meds because everything is getting redder on my skin. So yeah, let us gather and reconvene again tomorrow or the next day. Please do subscribe. That's true. Can we get 130 likes or 140 likes? Can we? Can we? Did you subscribe? Umair, Gocha, Jace, Abhimanyu, Richard, Whoop-de-doo. Have y'all subscribed? You better do it now. Adilo, Shake. See you tomorrow. It was great fun as always. Thank you. See you tomorrow, guys. Love you. Thank you for coming on and staying for the live. Really appreciate all of you. Thank you so much. See you tomorrow. Mwah, 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 mwah.
And also, if you're sleeping, keep on sleeping. Keep on sleeping. Go back to sleep, okay? And rewind and watch the whole live. I did 7K. Yes, whoop-de-doo. Mwah, mwah, mwah. Please do catch us live next time. I will see you soon. If you see our videos, clips, shorts, please do show them some love, some live love, some love. If you catch us live again, please do join. You should subscribe so you can find all our lives. If you're wanting to sleep to more such physics ASMR playing, you should go find all my other live videos under the live tab of the channel. There's many long videos and you should play them and get to know what we talk about on this channel. Love you so much and thank you for your support, guys.